Hello. Today we're going to look at the beginnings of complex numbers. So we know about real numbers, all of the numbers we've dealt with so far. But there's another type of number that we're going to introduce. So a complex number includes all real numbers, but it also includes numbers that involve the letter I, which for historical reasons is connected to imaginary, the word imaginary. So the reason why complex numbers were developed, or one of the reasons, is that we would often or sometimes end up with situations where we had the square root of a negative number. So we had the square root of a negative number. What do we do? Well, we used to just have to give up. We couldn't go any further. But what mathematicians said is, well, if we take a definition that helps us out in this situation, if we say that we're going to define a letter, I, which is the square root of -1, and we know we can break square roots up into stuff multiplied together. So if we had, say, -10, we could break that up into square root of -1 multiplied by the square root of 10, and we know how to deal with the square root of 10. So if we break stuff up so that we have the square root of -1 and just call it this variable I, can we do any useful maths with that? And it turned out to be an extraordinarily useful trick. It allows us to solve massive numbers of problems and ended up having very deep mathematical significance that we don't really get into, but you can look into it yourselves. It's a very beautiful and important area of maths. But from a practical point of view, this is the fundamental thing that what we are going to be doing is based upon. We have this new definition of a letter I, which is equal to the square root of -1, or often we will want to think about it as I squared would be equal to -1. And we would say that these are almost equivalent. They're not quite, because if we took the square root of both sides here, it would technically be plus or minus the square root of -1. This is the more fundamental definition, but we will use this one almost more often. Now, let's put this into practice and see where we have come across situations of these negative square roots before. So if we want to find the roots of this quadratic, we have y is equal to x squared minus 2x plus 2. The screen is going to become brighter now in a moment. This is that quadratic. And what immediately jumps out? Well, it doesn't have roots. It doesn't cross the x-axis, which is what it means to have roots. So what's going to happen here? Well, we know from our work in discriminants and from algebra that we are going to end up with what we have called complex or imaginary roots. And now we're going to look at how we can actually deal with those roots. So going back, we're going to, we aren't going to find any factors that work for this, so we're going to switch to the minus b formula. So we write down our a, b, and c. A is equal to 1, b is equal to -2, c is equal to 2. And we write down our formula from our log tables, minus b plus or minus the square root of b squared minus 4ac, all over 2a. We have what we're going to sub in and the formula we are going to sub into. As always, extremely important that we write those two things down right next to each other. Then we have x is equal to minus 2 plus or minus the square root of -2 squared minus 4 on 1 on 2, all divided, all of that now divided by 2 by 1. So 2 plus or minus square root of 4 minus 8, and we can immediately see our problem on the horizon. We end up with 2 plus or minus the square root of -4 over 2. So what do we do here? Well, up until now, we've had to just stop and say, okay, we got complex roots. Now, let's try and use our definition that we've got here. So that'd be 2 plus or minus, break this up, -4 would be 4 multiplied by square root of -1. I can break my square root up into the product of square roots. We've done that before, particularly with surds. And I know what the square root of 4 is. They won't always work out to be nice numbers like 2 here. So don't imagine that you have to get a whole number coming out of this. It would be 2, and I know that the square root of minus 1, by the definition I have introduced, is I. Now, I behaves basically the same as a normal algebraic letter when we aren't using this definition. So if we end up with I squared, we will turn it into minus 1. But if it's just I in a question, it will behave exactly the same way as if I had 2 plus or minus 2a, or 2x, or 2y. It just behaves like a normal letter. So I have a common factor of 2 top and bottom here. So I end up dividing out the top and bottom by 2, and I end up with 1 plus or minus 1i, which again, it's a normal algebraic letter. So it's just going to be I by itself means 1i. So I can see something interesting that has happened. My solution would be x would be 1 plus I, or x would be equal to 1 minus I. And if I cast my mind back to where I had something plus or minus something else, these two things are conjugates of each other. If we remember back to when we would want to rationalize a denominator of a fraction, we'd want to get rid of the square roots underneath a fraction. We ended up using conjugates, and conjugates are going to be extremely important in complex numbers, just as they were with surds earlier on. So we can see that we got a conjugate pair. We have 1 plus something and 1 minus the same thing. These are conjugates of each other. That's going to be important. Now, as I say, I just behaves like a normal algebraic letter, unless we end up with I squared for some reason, in which case we use this definition to turn it into minus 1. So let's put that into practice with a few different examples. So I have that written out for you here, and we have Z is going to tend to be used instead of Y or X for complex numbers, just to differentiate between real numbers and complex type situations. So if we're dealing with a real result of something, we'll tend to use X, which is why I started with X here, but really you would usually use Z if you ended up with complex numbers, and that's what I've got here. So I have Z1, this is just a number, just like X could be equal to 3, or X1 could be equal to 5. Z1 is going to be a complex number. This is all one number. Now, we have Z1 is 5 plus 2i, Z2 is 4 minus 3i. What is Z1 minus Z2? It's equal to Z3. Find Z3. So Z3 is going to be a third complex number that is the difference between these two. We'll often put brackets around these, or rather you will often see that done. So I'm going to do it here. This is just an algebra question. Now, these may as well be A's or X's. The I's will behave exactly like algebraic letters. 5 plus 2i. There's nothing multiplying this bracket. There's a minus 1 here. So we end up with minus 4 plus 3i. Minus by plus is minus. Minus by minus is plus. Now gather like terms. I'll put a different symbol underneath each one of them to keep track of what I'm on about. The connection between going with real and imaginary and imaginary, I again stands for imaginary, can be thought to stand for imaginary, is going to be important. So getting used to consolidating real with real and imaginary with imaginary is going to be important very soon. So that is what Z3 is equal to. It's another number. Now, I haven't done any labeling here. This is just multiplying two complex numbers. Again, it behaves exactly like the algebra you already know. So whichever way you multiply out brackets, 1 by 4 plus I plus 2i, 4 plus I, 4 plus I minus 8i. Remember, this is just like if you had minus 2x multiplied by 4, it would be minus 8x. Now, minus 2 by plus I. We have effectively a 1 here, so it's going to be minus 2. I by I is I squared. But that sets off an alarm bell in my head. I know something about I squared. It's minus 1. So this bit here is equal to minus 1. So I end up with 4 plus I minus 8i minus by minus is plus 2. And then I gather up my like terms just like I did before. 6 minus 7i. So that's how we can multiply those out. There's one more thing to look at when we're introducing the concept of I, and that is that there's a pattern. We can see that if we have I by itself, we don't do anything, it's just equal to I, and I squared is equal to minus 1. Well, as we go up in powers of I, there's an interesting pattern that occurs that we're going to explore before we finish. Okay, so I have written out a bunch of powers of I here. I by I by I by I, and so on down. I've written them out to show the link between each power and its preceding power. There are other ways of writing out this pattern. But what do we have? I to the power of 1 is just I. I to the power of 1 is just I. I squared is minus 1. I cubed would be minus 1 by I would be minus I. I to the power of 4 would be minus I by I would be minus I squared. Minus 1 would be 1. And then I to the 5 would be I by 1 would be I. And we can see that the pattern starts to repeat. After we go through power of 4, it's supposed to be a curly bracket. So after we go through a power of 4, or sorry, yeah, powers of 4, we end up starting to repeat again. We go I minus 1 minus I, 1. I minus 1 minus I, and the next one will be 1. And it will keep repeating every fourth power of I. So one of the things we can be asked, which can seem like quite an odd question on the surface, is what would something like I to the power of 17 be equal to? Well, if we recognize the pattern that every fourth power of I, we just revert back to the beginning of our pattern again. This effectively just becomes a junior cert patterns problem, when we would have been given a bunch of shapes and asked what would be the 30th shape in this pattern. This is effectively all that we've got here. It's just a little bit more abstracted now because we're looking at powers of things changing over time. So how many complete powers of 4 have we gone through when we're at I to the power of 17? Well, it would be I by I to the power of 16. 16 is 4 fours. So we've gone through 4 complete cycles of this pattern. So when we get to any power of 4, we just end up with I to the power of any multiple of 4 is going to be 1. So this business here is just 1. So find how many complete cycles of 4 you have gone through. All of the complete cycles of 4, regardless of how big they get, is just equal to 1. And then you're just looking for what I to the power of whatever is left over is, which in this case is just I. Now, if we were given a larger number, like I to the power of 58, for instance, I don't know how many complete cycles of 58 there are. My 4 times tables don't go that high. So what I can do, or maybe they do, maybe you can figure that out, but for me anyway, the easiest way that I would do it is divide 58 by 4 and see how many complete cycles I go. So when I have 58 divided by 4, I end up with 14.5. Sorry. 14.5. So I have 14 complete cycles and then a bit left over. So what I'm going to do then is multiply 4 by 14. So 4 by 14 will tell me how many are complete cycles. So I would end up with I squared by I to the 56. This is just equal to 1. So I end up with this being I squared, which is just minus 1. And that's how we can deal with our patterns of I. And that's what we need for now.